So this is the promised recording of the infrared and Raman techniques, so that I can spend the time after Easter doing some kind of examples and kind of spending time reading the papers. I'm going to split this recording up into maybe 3 or 4 sections, just so that you don't have to listen to me drone on for an hour. And I've also got a cold, so hopefully I can record in sections short enough that you don't need to listen too much to my snotty self. So this is kind of the very first stuff that I covered in the lecture last time, and so I kind of introduced you to infrared. And you've all used infrared before, and you've all seen Raman as part of your studies, whether that's with Steve Rosa in the second year, or I don't know whether you come across it anywhere else, but Steve definitely covers Raman, and he talks about it from a rotational and vibrational point of view. But right here, I'm only interested in vibrational Raman. So I quickly mentioned the structure of an infrared. Nowadays, most of them have a laser source rather than a scanning, a broad wavelength that we select. And we get the range of wavelengths by using this interferometer, which basically causes an interference filter, and I get patterns of constructive and destructive interference, which means that I can essentially select different wavelengths just by moving this mirror that's on the left-hand side. I've put my sample here in KBR discs, but normally nowadays it's in an ATR, which is just we put our sample loose down. And so we don't even need any sort of sample container anymore for infrared, other than the sheet that I put it down on. I have a photodiode as my detector, and that's kind of the basic building blocks of my traditional infrared, using an infrared kind of source, so an infrared or red laser to get my different wavelengths. The signal I get out needs to undergo Fourier transform, which is why we call them FTIRs. I'm not going to go into any of the Fourier transforms. Some of you that have perhaps done natural sciences will have seen Fourier transforms. The point of it is that I end up with a big mess of a signal, essentially, but that there is a single solution to it, which gives me the spectra. That is the only possible way that I could get that particular big mess of signal. So I'm just going to kind of refer to that as a magic piece of maths. It's a very clever piece of maths. But it's essentially the same way as an NMR works. I get a big mess of signal, and I have to use a Fourier transform to kind of deconvolute the data that I have. Here I have essentially a fluorimeter. This is kind of a sketch of a fluorimeter, but I already have mentioned that when we calibrate a fluorimeter, calibrate the emission from a fluorimeter, I'm going to use it by using the water Raman, because it's a very, very simple thing in order to calibrate my fluorimeter. But this gives me the basic schematic of how a Raman would work. I'm going to look at scattered light. I'm going to look at light coming out at 90 degrees from my sample, just like I would in a fluorimeter. And I'm going to have something to select wavelength, particularly on the emission. This is where we would see it in a traditional Raman, and that goes to a PMT. PMTs because they're incredibly sensitive. So Raman's a very low signal option, and so I need a very sensitive detector. Here I have a source of a xenon deuterium arc lamp. This is a perfectly acceptable option, and then using a monochromator to select single wavelength. But again, nowadays we tend to use a laser when we do Raman, but the fact that I'm showing you a fluorimeter means that we can actually get some basic Raman measurements out of a fluorimeter. So what do vibrational measurements tell us? Well, they give us information on the functional groups, and they can tell us a little bit about the structural basis of molecules, about the kind of rearrangements and the geometry that things are taking within a molecule. The problem with infrared is that we know that it's best for small molecules, that infrareds can become very, very complicated if I look at anything other than small molecules. It's not very good for looking at kind of excipients, extra things in my samples, so it can't identify impurities, so everything just gets confused. It can tell me really well that I have a carbonyl, or I have some CHs, or I have an aromatic, but telling me how much of it I have and telling me whether it's attached to my main molecule that I think I'm looking at or just something else that's in there is a real kind of limitation of infrared as we currently use it in the lab. One thing that I will say is that there are different types of infrared spectroscopy, that we've probably only really considered one or perhaps at most two of these different techniques before. I'm just going to mention those briefly now. Excuse me. So our traditional infrared, we look from 4,000 to 600 wave numbers. Normally I discount anything below 1,200 wave numbers. So I record it 12 to 600. Normally I discount it. The reason being that's our fingerprint region. It's very, very difficult to interpret. It's unique for a molecule, but it's difficult to interpret. But this is kind of the 720, we're picking out a carbonyl type scenario that we have. It can sometimes be referred to as mid-infrared spectroscopy, but it's really good at identifying functional groups. It can show some kind of really basic information about my molecule. Traditionally, this was done with KBR plates and making up Mujol, which was slightly troublesome. KBR is air sensitive, it's very sensitive to water in the air. And it was kind of an extra kind of step to the analysis. Nowadays KBR, which is transparent to infrared, which is why it was used, but nowadays KBR has kind of been ousted in favour of ATR instruments. So ATR stands for attenuated total reflectance, and what this is essentially doing is just putting a sample straight down on the crystal and pressing it down so we get a good kind of signal from it. I'm sure you've all used ATR instruments, and if you haven't, you're more than welcome to pop into the lab sometime and see our ATR. So a different type of infrared we have is near infrared, which looks at higher energy, so looking much more just at kind of just past red light. There are different types of near infrared instruments. Some of them work very much like an absorption instrument, and you put in a thin film of your sample. Others are looking at backscatter from a sample, which is a really, really useful way of going about it. So in this case, we can look at either overtones of fundamental transitions, but the thing about near infrared, it behaves a lot more like an absorption instrument. In other words, I can get quantitative information off it. If I use a reflectance technique, what essentially I'm doing is I'm putting light into my sample, and I'm going to measure the light that gets scattered back from my sample. But some of that light will have been absorbed, so the backscatter I see has kind of regions of intensity which have been absorbed, which are lower. In other words, I'm looking at information just as if it had travelled all the way through my sample, even though I'm looking at scattered light. It works very, very similar to a traditional absorption machine. So this is near infrared, and as I say, it can give us some additional information. And as you can see, I've converted it here to wavelength. This is just outside the red. I can also look at far infrared. So this is looking at very, very long, low energy wavelengths. This has been used in inorganic. Metal to ligand bonds show up here, but it's very, very rare, very uncommon, quite specialist. So I've mentioned it happens, and that's all I'm going to say about it. But I suppose what I'm trying to say is that there are many, the infrared region is quite big, and we can use different parts of it to do slightly different techniques. The other spectroscopy that I was going to talk about today is Raman. The two go hand in hand in that they both look principally at vibrational energy levels within molecules. Raman can also be used to look at any other energy level within a molecule. Rotational is quite common from a theoretical point of view, but tends to be used less nowadays. Most Raman that we see is vibrational Raman. Venkata Raman, discovered this technique way back in the 20s. He won his Nobel Prize for it in the 30s. And it was a curiosity for a very long time until lasers came to the forefront. And lasers is the really important thing with Raman. What we need to have is we look at the small scatter, the small difference in the wavelength of incident and excident light from a sample. So I need to have very, very monochromatic light coming in, which lasers afford me. But the other thing is that Raman is quite a low intensity technique. So for fluorescence, if I have a fluorescence quantum yield of 0.4, that means 4 in every 10 photons are coming out as fluorescent photons. So 4 in 10 is quite a lot. Whereas when I'm looking at Raman, I'm genuinely looking at 1 in a million. So 1 in a million photons that goes into my sample will be scattered Raman light. So that's a very, very low intensity problem. And that gives me some problems in measuring it, some difficulties in measuring it. So even though Raman had discovered this way back in the 20s, it didn't really come into prevalence until the 70s or 80s when lasers started to become much more common. So if I do a side-by-side kind of comparison of infrared and Raman, we can see that I have my infrared, that's an absorption technique. Raman is scattering. I have 2 selection rules. I've not mentioned them so far, but if you've done stuff with Steve, you'll have heard these before. So for infrared, I have that there must be a change in dipole upon absorption of a photon. For Raman, there has to be a change in polarizability for my transition to occur. My light sources, traditionally with infrared, I used a thermal source, some infrared emission. Nowadays it tends to be a laser combined with an interferometer. Raman spectroscopy uses a laser. It's the only kind of thing that will give me the intensity of the light, but it doesn't need to be an infrared laser. It doesn't need to be a red laser. It can be any wavelength of laser because I'm looking at a scattering from the thing. And instead of using an interferometer, if I'm not using a laser source, I would have a monochromator, but if I'm using a laser source, I wouldn't, but I need to have some sort of excident monochromator regardless. So I need to be able to kind of select the wavelength of the excident light regardless of the incident light wavelength. My detector for an infrared is a photodiode. Photodiodes work very, very quickly. I can collect a lot of information very, very quickly. However, a PMT gives me the low-level signal that I require for my Raman technique. So Raman always uses a PMT. And with infrared, once upon a time I used to use salt, so KBR being the classic thing. Now there's kind of no formal containment. It's just a crystal press that's kind of having my sample in for infrared. For Raman, I can use any transparent material, and that just means matching the incident light and the transparency of that material. So I could use quartz, I could use glass, but I could also use plastic if I've got the right wavelengths as well. So really, really versatile. Raman is incredibly versatile. So this is where I'm going to finish this first of these kind of topics, just to keep them short and sweet. Number 2 will be coming up imminently.